Hello, welcome to The Naked Scientists with me, Chris Smith, and also with Ginny Smith. Hello, Ginny.
Hi there. Now this week we want to hear how you're doing with your New Year's resolutions as we investigate the psychology of willpower and how long it takes to form a new habit. Plus, in the news, does drinking a cup of coffee after studying help students remember their work? And new super thin electronics that could help monitor glaucoma.
And we also always set you a little tea time teaser to accompany the programme. This week's no exception. Nicotine. We've been talking about New Year's resolutions. People want to kick the smoking habit. The reason we smoke is to obtain nicotine if we're hooked on it. That's why we want nicotine. But why do the plants that make tobacco make it? What's the point of nicotine for a plant? Let us know what you think. Any thoughts, comments, questions or feedback to The Naked Scientists, chris@thenakedscientist.com or tweet @nakedscientists.
The Naked Scientists podcast is powered by ukfast.co.uk.
Well, let's kick off and take a look at some of this week's hot scientific breakthroughs. Ginny.
So I found a story this week about caffeine, and being as in the Naked Scientist office at least, caffeine is a big part of our day, I thought that might be quite an interesting one to look at. So people have used caffeine to help them stay awake and study for exams for a very long time, but this new research by Daniel Barota and colleagues says that it might actually be doing more than just keeping you alert. Their paper, which was published in Nature Neuroscience this week, shows that caffeine can actually help you remember information. So what they did was they got some people in and they asked them to categorise a load of pictures into things you use inside or things you use outside the house. And that was just a trick to get them to look at these pictures and pay attention to them. And then they gave them either some caffeine or a placebo. 24 hours later, they brought the people back, showed them another set of pictures and asked them to identify whether each of these pictures was old, so they'd seen it the previous day, whether it was new or whether it was just similar to the ones they'd seen the day before. Now, they found that both the groups that had been given the caffeine and the groups that had been given the placebo were pretty much equally good at categorising the old and the new pictures. But those who'd had the caffeine were better at recognising pictures as similar. So it suggests that the caffeine that was given after they'd first seen the pictures helped them form sort of clearer memories, which is a process known as consolidation, that sort of storing of memories. They also tried giving caffeine before the test, so the day after the study session, but they found that had no effect. It has to be given right after you've looked at the pictures. What they then went on to do is try different doses of caffeine, and they found that 100 milligrams, which is about one shot of espresso, had no measurable effect. You needed 200 to 300 milligrams to get this improvement. So it's several shots of espresso you'd have to be drinking.
Even by my standards, that's quite a lot of coffee, but not unfeasible. So people probably are, especially mathematicians and computer scientists, probably are boosting their memory this way, I would think.
Yeah, they probably are, and we're not quite sure why it works. There are a few different mechanisms they suggest. We know that caffeine works in the brain to block something called adenosine, which is what makes you sleepy, and that's why caffeine gives you that sort of boost. But this might also prevent the adenosine from inhibiting noradrenaline, which in turn might improve the consolidation, or they think it might act directly on some receptors in the hippocampus, which is a very important region for memory, or possibly some other regions. They're just not quite sure yet. That's sort of case for further study to work out how exactly it works. But for the moment, it seems like it might be quite useful.
I should certainly not cut down the coffee, that's for sure. It also resonates with quite an interesting story which came out almost this time last year by researchers at the University of Newcastle, and they did a study where they showed that bees are probably being hooked onto plant caffeine in order to crystallise a memory in the bee's mind of what plants it's pollinated. So the experiment they did was they gave bees some sugar solution and presented the sugar solution alongside a smell, and they also laced one of the sugar solutions with caffeine, because someone had found that if you look at the nectar in a plant, then the nectar in the flowers of that plant is producing caffeine at a concentration similar to if you were to go and have a shot of espresso down the coffee bar. So it's quite a high dose. And what they wanted to ask is, well, would the bees remember the smell, giving them a sugary reward better if it was laced with caffeine at the concentration you find in a flower, or not? So then they sent these bees away after they trained them, gave them 24 or 48 hours, then retested them. So basically you present the smell and the sugar solution again and see which of the things the bees go for, whether they go for the smell and the sugar or a different smell. proving whether or not they've actually formed a memory for that smell as giving them a sugary reward. And there was a 100% improvement in bees going straight to the smell that they'd learned previously in association with caffeine as giving them a sugary reward. And they then looked in the bee brain, and there are certain structures which we think form memories when nerve cells change the strength of their connection in the bee's brain. And they found that the presence of caffeine strongly increased what they call long-term potentiation in the bee brain, boosting the formation of memories in that part of the brain that it uses to remember things. So it's certainly worked in bees. So it looks like the same is probably true in people.
Yeah, it would be fascinating to know if it was the same mechanism and if it had been preserved throughout evolution or if it had evolved twice in bees and humans.
But of course, for the bees, the plants make the caffeine because they want the bee to form a strong memory of the smell of their flower and them, so that then bees will go and find another plant with the same smell and pollinate that one too. So what's the subversion in humans? Is it working on us because we therefore look after the coffee plant and treat it very nicely so we make more coffee plants?
Possibly. I guess it probably gives the bee more energy as well, so it can fly further to find more plants as well. But yeah, hopefully we'll find out a bit more about this in the future.
I shall certainly stick to the coffee. Thanks, Ginny. Well, look, you've talked about caffeine. I'm going to talk about booze, because you might remember last year, and this really is a longer term story, and I would like your opinion and also the opinion of people at home on this, because last summer, you might remember there'd been all this talk about introducing a minimum price for alcohol. The idea being that we know how much alcohol costs. If we had a minimum price set for a unit, that this might deter people who are problem drinkers. And it looked like it was going to be introduced into law, and then it was suddenly thrown out. Well, the British Medical Journal have this week devoted both an editorial, a big investigative piece to this by a journalist from Essex, actually, and also there's quite an interesting commentary written by a couple of researchers from Britain. And it puts the case for why we ought to have a minimum price for alcohol. And what I thought I'd do is just read this to you and see what you and people at home think about this. So this is by Nick Sherron, who is a clinical hepatologist, so a liver specialist from the University of Southampton, and also a lady called Kate Eisenstein, who is the senior policy advisor for the Royal College of Physicians in Britain. And they say the mean weekly alcohol consumption of patients with alcoholic cirrhosis is around 15 bottles of white wine or 5 bottles of vodka, 20 litres of super strong lager, or 20 litres of strong white cider brewed with fructose. That's per week. As a result, irrespective of income, these very heavy drinkers tend to opt for the cheapest possible alcohol, which is currently about 30 pence, that's about 50 cents in Australian or US, per unit. The average low-risk drinker, so that would be someone who goes out for a social drink, perhaps like you or me, already pays around £1 for a unit of alcohol because they're presuming you're a bit more discerning, Ginny. You don't go for the low-cost strong stuff. And so the impact on low-risk drinkers, they say, is negligible. And on pubs, it's zero because people are already paying over that cost anyway. They then go on to say a minimum price of 50p per unit of alcohol would mean that a 700ml bottle of vodka with a typical alcohol level of 40% would cost £14, which would make it difficult for the heaviest drinkers to maintain their alcohol consumption without a significant increase in their expenditure. Then they go on to say, well, look, we acknowledge that all purchase taxes are regressive. In other words, if you tax things more, the poorest people are going to pay more tax, so it's going to hit the poorest harder, which is always a concern. But then they say, the effect of alcohol-related harm on deprived communities, though, is savage. There's a threefold excess mortality between the most deprived and the least deprived socioeconomic groups. And they then go on to say, and this for me really crystallised it, taxpayers are already paying for the harm that alcohol causes. According to the Organisation for Economic Cooperation and Development, alcohol misuse currently costs the UK 2 to 3% of gross domestic product. The turnover of Britain, that's a huge amount of money. This equates to around £12 a week for each of the 60 million or so UK inhabitants, of which only £3 comes back from the drinks industry in taxes. So that means moderate drinkers and non-drinkers in the UK are subsidising heavy drinkers to the tune of around £9 a week. The alternative to minimum pricing is a general increase in alcohol duty, and it's precisely because minimum unit pricing is so targeted that it's so effective. In Canada, where they had a minimum unit price for years, a 10% increase in the minimum price resulted in a 32% decrease in directly attributable alcohol-related mortality. Sounds compelling, doesn't it?
It does, yeah, particularly that last statistic, because before that I was thinking that It might make some people stop drinking, but the people who are really hooked, they're going to find ways of getting that money, and they might resort to crime, or they'll end up not having enough money to eat because they're spending it on the booze. But the statistics from Canada seem to suggest that that's not as much of a problem as I thought it might be.
Yeah. But I still remain slightly concerned that we might end up with some people who will just sacrifice everything and then also supplement with some crime to top up. So I think there's always a worry, but it does appear that you can achieve quite dramatic reductions with this sort of intervention. I would be interested in what people at home think as well. Do you think we should have this, and why did the government sling it out? The British Medical Journal have evidence here suggesting they think it's because there's some kind of interaction between the government and the drinks industry, and they've been lobbied to reverse the decision. I think it would be actually, in my view, quite a good idea.
Thanks, Chris. This week, hell literally froze over as the small Michigan town of Hell experienced temperatures of minus 17 degrees. And Hell wasn't alone. Temperatures across the United States have plummeted to record lows as cold air from the Arctic has reached much lower latitudes than usual. Here's your quickfire science about polar vortices with Kate Lamble and Dominic Ford.
Around the Arctic and Antarctic, air rotates in structures called polar vortices, which mix very little with air at lower latitudes.
In Antarctica, this mass of air is so enclosed that very little warm, wet air ever blows in, with any likelihood of forming rain.
As a result, only a few centimetres of snow fall across Antarctica every year, meaning that much of the continent is actually classified as a desert.
A similar Arctic polar vortex is normally centred around Baffin Island in northern Canada.
But in recent days, a weather system over the Pacific has pushed northwards, forcing part of the polar vortex south over the US and Canada.
In North Dakota's largest city of Fargo, this has led to temperatures plunging as low as minus 35 degrees centigrade, cold enough that frostbite can set in even underneath clothing.
In Indianapolis, meanwhile, all non-emergency driving has been banned and people have been urged to stay indoors.
In 2010, it was a similar migration of the Arctic polar vortex, which led to incredibly harsh weather across Europe.
As the fast-moving belt of air which serves as the boundary between warmer southern air and cold polar air is driven by temperature differences, it weakens when the Arctic is at higher temperatures.
The Arctic is currently warming more rapidly than lower latitudes. And White House science advisor Dr. John Holdren argues that this makes the polar vortex's boundary less well defined, increasing the chances of cold air passing over the US and Europe.
As a result, he argues that global warming could, rather counterintuitively, lead to more extreme cold spells like this in the future.
Kate Lamble and Dominic Ford. And you can get hold of all our Quickfire Science episodes as their own podcasts from our website at thenakedscientists.com/quickfirescience.
Certainly feels like we've got a polar vortex round here. It's absolutely freezing today. Now, you're listening to The Naked Scientists with me, Chris Smith, and also with Ginny Smith. If you'd like to get in touch, and remember we have a quiz running this week, we're asking you, nicotine is the addictive thing that people smoke tobacco to obtain. It comes from tobacco plants, but why do plants make nicotine in the first place? If you think you know the answer, you can email chris@thenakedscientists.com, you can tweet @nakedscientists, or you can find us on our Facebook page. That's facebook.com/thenakedscientists. When surgeons need to operate on things like the heart and the cardiovascular system, minimally invasive procedures are often the best way to avoid complications and to reduce recovery times for patients. But if you reduce the space you're working in, then you also reduce the space you have to use things like sutures and staples. Well, our team has developed a light-activated, blood-resistant glue for use in just these scenarios. Jeffrey Karp from Harvard Medical School is the co-inventor. Hello, Jeffrey.
Hi, how you doing?
Very well, thank you. So what is wrong with the glues that currently surgeons and doctors have to use on tissue? Why do you need to invent a new one?
Sure. Well, we've been using staples and sutures for decades, and there's been really minimal innovation. They have inherent limitations. As you mentioned, they're difficult to place in small spaces like during laparoscopic or minimally invasive procedures. Also for glues, there's very few glues that actually have been approved for medical use. And one example of a glue that's approved is a medical-grade crazy glue or super glue, and it's only been approved for minimal uses. And when you use it inside the body, you actually have to dry the tissue before you apply it because it's just so highly reactive. And so this essentially means you can't use it for most applications that clinicians would like.
So what inspired you to solve some of those problems and come up with this new glue?
So I've been working closely with Dr. Pedro Del Nido, who's the chief of cardiac surgery at Boston Children's Hospital, and he's been trying to seal septal defects, which are holes that occur between the chambers of the heart. And 1 in 100 babies that are born have some form of congenital defect, and the ones that require surgery, typically a non-degradable device is put in, and then it needs to be changed every few years because it just doesn't grow with the patient. And so what we were interested in doing is coming up with a new type of adhesive that would allow us to seal these holes using fully biodegradable materials that would work in the presence of blood in such a challenging environment inside the heart. And so what we did initially is we came up with a long list of design criteria for a solution, and we wanted the material to be biodegradable. We wanted it to be elastic because the heart continuously expands and contracts multiple cycles. We wanted it to be non-inflammatory, so when we would implant it, it wouldn't promote a strong inflammatory response. And then we also turned to nature for some inspiration. So if we look into nature, there's many examples of insects and other critters on land and even in the ocean. And what we noticed is that if you look at these collectively, many of these creatures have secretions, and those secretions are highly viscous. And so when they are placed onto a surface, they don't really move too much. And if you look carefully at these secretions, they also contain agents that repel water. And so what we thought would be, could we develop something that would initially be very viscous, kind of like honey, but then also repel blood and water away from a surface. So as soon as you applied it to tissue, it would repel the blood away from that tissue, and then it would stay there, even in flowing blood conditions such as inside the heart.
And how would you deploy it? So if you had a defect in the heart, as you've outlined in these children, how would you get the glue into the right place and then make it set?
So this is something that we've thought quite a bit about. So we designed this glue with that in mind. So the idea is that because it's viscous, it's in a liquid state, so we can inject it, we can even paint it on, we potentially could spray it, and we've also shown that we can place this onto the surface of a patch-like material, and then we can deploy this. So in some instances, we may use the glue alone by injecting through a minimally invasive device, for example, and in other instances, we can coat it on the surface of a patch, and even a biodegradable patch, so the entire system, the glue and the patch, will degrade.
How sticky is it? Because the pressures generated, for instance, in the heart or an artery are extremely high. Can it withstand that?
Absolutely. So that was one of the other design criteria, is that not only do we want this to stick, but it needs to be strong enough to close holes in these dynamic environments. And so in one example, we actually created a hole in a rat heart, and then we were able to seal it. So it was a sizable hole in the heart of the rat, and we were able to seal that with just pure glue alone. And we took the animals out to 6 months, and they did fine.
And is there not a risk that this stuff, being very sticky but also being very gelatinous, could break off from where you've deployed it and then go down a blood vessel and effectively block up a blood vessel, therefore depriving the tissue downstream of oxygen and blood flow?
Sure, there's always these types of risks exist, but what we were able to show in our studies is, first of all, we didn't see such instances of these types of complications occurring, and also these materials are very biocompatible, and so what that means is that cells and tissue can grow over them very quickly, and so right after we place this glue into the heart or onto the surface of a blood vessel, for example, within just a few days it's already starting to be coated with cells and other tissue, and so that will significantly limit the potential for chunks to break off, as you say, and cause an embolism or a stroke.
And how do you actually make the glue set where you want it to?
What happens is that wherever we inject the glue, as soon as it hits a surface, because it's so viscous, it just stays there. And then what we found, which was quite fascinating, is that the glue is able to penetrate into the tissue. So it actually goes into the tissue fibers. And then when we shine UV light, this actually cures and locks the glue into place.
And there's no danger to the tissue through having ultraviolet light shone on it?
We've shown that we can shine a fairly low level of intensity of light over a short period of time. So it only takes maybe 5 to 30 seconds to get a complete cure. So in our initial experiments, we actually looked at this in extensive detail and found intensities of light that did damage the tissue, but then we were able to scale that back and it still achieve a strong, fast cure without doing damage to the tissue.
Sounds wonderful. We look forward to being able to use it. Thank you very much, Geoffrey Karp from Harvard, for joining us. He published that work this week in the journal Science Translational Medicine. Ginny.
So another story that caught my eye this week was from researchers at the Swiss Federal Institute of Technology, who found a way to make some super thin and flexible electronics which can be applied to almost any surface. So they published this paper in Nature Communications, and these thin film transistors, they're machined onto a film of a polymer called parylene, which is only 1 micrometre thick, so that's 1/1,000,000th of a metre. It's really thin. Now, they have to hold that film in place while they're doing the machining. So to do that, they attach it to a piece of silicon. Now, the clever bit is that they use a special glue to attach the film to the silicon that's soluble. So that means once they've made the transistor, they can just pop the whole thing in some water, the silicon wafer falls off as the glue dissolves, and you're left with this film floating on the water, which can then be picked up and applied to all sorts of different things. Giovanni Salvatore and colleagues who did this paper, they chose parylene because it's biocompatible and it can be attached to a huge variety of materials, from textiles and implantable devices to plant leaves and even human skin. And that means they've got a huge range of possible applications for this thing. They even made both transparent and non-transparent versions of the transistors, so that widens their possible uses even further. They wanted to show how flexible the devices are. So first of all, they bent them over human hairs, which doesn't sound like much bending, but when you're only 1 micrometre thick, that's quite a lot of bending. And both of them survived that and still worked absolutely fine. They then tried putting them on a piece of foil and then crumpling the foil up and flattening it out again several times. The transparent one didn't work, but the non-transparent one actually survived even that, which is quite impressive.
What do they say we could do with this medically? What are the sort of future goals of doing this?
So they think there's a huge number of goals, but one that they actually tested out was using it on a contact lens. Because it's so thin and light, and because they made the transparent version, you can actually apply it to the front of a contact lens. And they did that and then put it into an artificial eye. They haven't actually put it in a real eye yet. And they showed that it still worked. So what they think this could be useful for is monitoring eye diseases like glaucoma, because you can put a sort of stress sensor on this plastic contact lens that can detect changes in eye shape that are a problem.
So when the eye swells because of the pressure going up in glaucoma, it could register that and then give a person an early warning, because the problem with glaucoma is you don't know that this is happening to you and you could be damaging your sight without realising it.
Exactly. It can send them probably a text message to their phone to go and see a doctor and get this dealt with.
That's fascinating. Ginny, thank you very much. That's Ginny Smith. I'm Chris Smith, and this is The Naked Scientists. We're talking about habits, habit forming, and keeping New Year's resolutions, and that's what's coming up in a second. If you've got a New Year's resolution, we'd like to hear about it. What was it? You can email chris@thenakedscientist.com, or you can tweet @nakedscientist. And if you have any questions, we've got a lineup of people who are going to talk about how you can successfully give things up or not this week. Tell us what you're trying to give up. We'd love to hear from you.
Our first guest tonight is Molly Crockett from the Wellcome Trust Centre for Neuroimaging at University College London. Hi there, Molly.
Hello.
Now, as part of your work, you investigate willpower, and that's something that everyone needs when they're trying to stick to their New Year's resolutions. It's so difficult to resist that tempting bar of chocolate when you're trying to eat healthily. Why is it so tricky?
Well, it's a classic example of a conflict between our long-term goals and our short-term goals, and the problem is that when we're trying to resist a temptation that's right in front of us, that short-term goal is really smacking us in the face, and the long-term goal is more distant in our minds.
So we've got the short-term goal of chocolate's tasty, I really want to eat it, and that's almost overpowering our long-term no, I'm trying to be healthy, I should be eating my greens, that sort of thing.
Exactly.
What parts of the brain are actually involved? Are there two different bits that are trying to take over?
Well, generally, we see willpower in the brain as involving a competition between brain structures that are involved in reward processing, including the ventral striatum and the medial prefrontal cortex, and brain structures that are involved in self-control and sort of inhibitory control, and that includes the more lateral aspects of prefrontal cortex, including the dorsolateral and inferior frontal gyrus.
So is there anything we can do to make it easier for ourselves if we are trying to stick to a New Year's resolution? What can we do to prevent the temptation from taking over?
Well, we've done a number of studies looking at this, and willpower is, of course, the main strategy that we think of when we think about self-control. But it turns out that there's another strategy that we can use that actually can be more effective than willpower. So willpower, of course, is when we're using our self-control to resist something that's right in front of us. But there's another strategy called pre-commitment. And that's when we take steps now to prevent our future self from being exposed to temptation in the first place. So the best example of this is if you want to avoid eating unhealthy foods, you just don't buy them at the shop in the first place so that they're not even around to tempt you. And we've done some experiments to show that pre-commitment can actually be more effective than willpower when you're trying to reach your goal.
So how do you do an experiment to look into something like that?
Well, our experiments were inspired by the classic studies done several years ago by Walter Mischel. In those experiments, they looked at how little kids were able to resist eating a marshmallow that was sitting right in front of them. We wanted to do a study in adults, and we focused on young men, and we didn't think that marshmallows would be as tempting for the young men. So instead of using marshmallows as temptations, we used enjoyable pictures of women. And these pictures, we had the men rate them before the experiment. So we had a large set of pictures. Some of them were just moderately enjoyable, and some were extremely enjoyable for them. And then what we did was we gave them a choice. They could see a okay picture now, or they could wait, and after a delay, they could see a highly rated picture. And we looked at how they made those kinds of choices in different settings. In the willpower condition, they had to basically wait for the large reward, the really enjoyable picture, but they had the option to choose the small reward, the less enjoyable picture, at any time. However, in the pre-commitment condition, before they were faced with the temptation, we asked them, would you like to pre-commit to see the large picture? So they had the option to basically remove the temptation from their choice space. And what we found is that when they had the option to pre-commit, many people did, and this made them more likely to receive the picture that they wanted the most than when they had to resist the temptation sitting in front of them.
And was that the case for everyone? Was it quite standard, or did it vary a lot from person to person?
Well, it varied a lot from person to person, both for willpower and for pre-commitment. So we had a lot of variability in our sample. Some people were really good at resisting temptation, and some people were less good at resisting temptation. And that was, of course, correlated with pre-commitment. So we can think of a general self-control skill that can be deployed in either willpower or pre-commitment situations. But interestingly, when we looked at the benefit that people received from the opportunity to pre-commit, so how much receiving the large reward improved when you had the opportunity to pre-commit, those benefits were actually stronger for the people who were worse at self-control, which makes sense, right? They had more room for improvement. But what was interesting was we also saw differences in the brain when we compared people with high and low willpower.
And what kind of differences did you see?
Well, what we found was specifically when we gave people the opportunity to pre-commit to a large reward, those people who had the most trouble with willpower showed stronger activation in their reward networks when we gave them the opportunity to pre-commit. So it was almost as though the brain could sort of sense the benefits of pre-commitment when you're making this decision.
So if you're someone who really struggles with willpower, then it's very important to do this pre-commitment thing to make sure you don't buy the unhealthy foods, you don't allow yourself that time to give in to those urges. Is that what we're getting from this?
Exactly. And I think the really powerful message here is that self-knowledge can go a long way in helping you achieve your goals. If you can recognize that you're really bad at willpower, you're not doomed to fail in reaching your goals. It just means that you have to take some steps to make sure that you don't face with the temptation.
Brilliant. Thank you so much, Molly. Molly, you're going to stick around, aren't you, and answer any questions from the audience that come in later?
Yeah, sure.
Great. Thanks to Molly Crockett from the Wellcome Trust Centre for Neuroimaging at UCL.
When I was a student, my now wife had a poster on the wall of her room, and it's a little kitten, and there's a goldfish bowl with a big goldfish next door to it, and the kitten's dipping its paw into the goldfish bowl, and the legend underneath said, "I can resist everything except temptation." Puts it very well, doesn't it? This is The Naked Scientist with Ginny Smith and with Chris Smith. We're talking about the question of willpower. We're talking about giving things up, habits, and all of those sorts of things related to New Year's resolutions. So have you made a New Year's resolution? Do tell us. We'd like to hear some adventurous or exciting ones. If you'd like to get in touch, you can email chris@thenakedscientist.com, or you can find us on our Facebook page. That's facebook.com/thenakedscientist. Now, New Year is classically a time when we make resolutions to give things up, usually things we regard as bad for us, like some kind of habit. And we do tend to think of habits as generally bad things. But actually, if we didn't have the ability to form habits, we wouldn't be able to learn anything, and life would be a lot more difficult. And what Cambridge University addiction researcher Barry Everett believes is that when we get hooked on things, this is just as much about the environment triggering us to behave a certain way as it is about the chemical addiction itself.
Every day when I was living in my previous house, I would come out of the house in the morning, turn right, turn left, walk along Regent Street, through the main gates of Downing College into my department. And I would do that every day, and I will be thinking about the weather or what I was going to teach when I came into the department or whatever. On Sundays, I wouldn't be coming into work. I would be going to buy the Sunday newspaper from the local newsagents. So I come out of the house and turn right and then go to the shop and turn around and come back again with the newspaper. But on numerous occasions, I would find myself somewhere along the route to the department, or indeed even in my office in the department, turning on the computer working, without ever having had any goal of coming to work. My goal was buying a newspaper, but the automatic elicitation of my sequence of movements that bring me to work was clicked into gear by the stimuli that control our repeated movements.
Do you know how many people you have made incredibly happy by them knowing that even the professor of psychology at the University of Cambridge does what we all do? I mean, I've driven down a road, got somewhere, and then have no recollection whatsoever of going over multiple traffic lights or junctions. It just happens automatically. How is that behaviour established in the brain? What bits of the brain are driving that? How does it work?
Actually, the key breakthrough here came from experiments in rats in this department some years ago by taking a rat that was hungry and putting it in a little box where it could press a lever to get food. So imagine looking at that animal, you would attribute goal-directedness in the animal's behaviour. Why is it pressing the lever? It's pressing the lever because he learns it delivers food. Why is he working for food? Because he's hungry.
So my suggestion would therefore be that as soon as the rat has eaten the food and is no longer hungry, he's going to stop pressing the lever.
Exactly. And you can devalue the outcomes. Let's imagine the rat's working for nice, tasty chocolate pellets. Instead of just doing that, this hungry rat, you give it access for an hour to unlimited sources of chocolate. So it eats chocolate till it can't move anymore. So the last thing it wants is chocolate. That's called devaluation. But if trained for a long time to do this, the animal will carry on lever pressing. It's not lever pressing for food. It's pressing a lever because through repetition, it's learned that when it goes into the box, the stimuli of the box and the lever causes it to press a lever, and the food may not be a desired outcome. And indeed, in this case, the food will be left, although the animal continues to respond for it.
And this is the rat equivalent of you coming out of your house on Sunday and instead of going to the paper shop, end up at your desk in the department. You did want to go to the department to do some work, really, didn't you, Barry? Just to be honest.
Exactly.
So where in the brain is that happening, and what circuits are making it possible for the brain to learn and establish these complex behaviours in this way?
Well, in imaging studies in humans, we can actually see the neural circuitries of that kind of learning. There's a particular part of the brain called the striatum. One particular part of the striatum, called the dorsal lateral part of the striatum, is crucial for enabling that transition from goal-directed to automatic behaviour. And in fact, if you inactivate temporarily that bit of the brain, animals are forever goal-directed.
So are you sort of saying, in the same way that the rat presses the lever for food in the box because he's in the box, the person who smokes a cigarette isn't just hooked chemically on the cigarette, but the environment that goes along with having the cigarette provokes them to also want to seek that drug?
Good question. With smokers, it's an interesting one. Particularly in this New Year period, many people will have said, I am going to stop smoking, but they find themselves after a meal, in a bar, with friends, outside their place of work where smokers congregate to smoke, and despite having the firm goal-directed intention not to smoke, suddenly find themselves with a cigarette in their hand and smoking. And drinkers will describe the same thing. And many people addicted to drugs like cocaine and heroin will have every intention not to do it. All of their conscious, effortful processing is on not lapsing, but the power of the environmental stimuli when they're in drug-taking settings just elicit those behaviours so they find themselves doing it automatically.
So that's the sort of habit side of it. But what about the actual physical dependency on the drug? Where's that rooted through the brain, or is that all part of the same system?
There are two sides to addiction. There's the positive incentive pleasure of taking drugs, and there's also the negative downside of withdrawal. And there are now growing amounts of data in the literature which suggests that the aversive nature of states like withdrawal can more powerfully drive the development of habitual behaviour than even positive incentive states.
Because a lot of people say, I take drugs not because it's pleasurable anymore, but it's medicine. It stops me feeling bad.
Yep. And so in a withdrawal context, again, when someone might be trying not to take drugs, the aversive state is able to engage that automatic mechanism more readily than otherwise.
Barry Everett from the Department of Psychology at Cambridge University. And I hope Richard Hughes, who got in touch via Facebook, facebook.com/TheNakedScientist, he asked, is there a difference between a habit and an addiction? I hope that what Barry was saying there rung true for you. It sounds like basically, from what Barry's saying, that an addiction is a spin-off of our normal behaviour, the way we go about learning about the world around us and reacting to it. This is The Naked Scientists with Chris Smith and with Ginny Smith. We're talking about resolutions, willpower and the psychology of how we actually kick habits this week. We've got a few suggestions of people's resolutions coming in. Stephen Ashworth has tweeted at Naked Scientist, top of my list is to complete the old year's commitments first. Ginny.
So let's say that I can use my willpower or a pre-commitment strategy to resist chocolate this year, and I try to eat, say, my healthy greens instead. Now, how long do I need to keep doing that before it becomes a habit to eat healthily and I stop having to think about it all the time? To try and answer that, we're joined by Ben Gardner from the Health Behaviour Research Centre at University College London. Hi, Ben.
Hello.
So I want my healthy eating to become a habit this year. What I mean by that is that I want to do it a lot and I don't want to have to keep thinking, oh, I really should eat my greens every day. But what does the word habit mean to you as a psychologist?
Well, it's an interesting question, actually. I mean, in the colloquial sense, habit is used to refer to, anything that we do repeatedly that's stable and persistent over time. But within psychology, we use the term in a slightly different way. And as a couple of your previous speakers mentioned, we refer to habitual behaviour as behaviour that's elicited automatically when we encounter a particular situation. So if you do want to get a new behaviour up and running, then this perspective would suggest that you repeat it so often that the behaviour becomes automatic. And the way that it becomes automatic is through repeatedly doing the behaviour in a given situation so that an association develops between the situation and the behaviour, and that association becomes so strong that subsequently encountering the situation is sufficient to prompt your behaviour without you really needing to think about it. That's when we'd say it's become an automatic behaviour.
So if I want to get into the habit of eating an apple in the afternoon, what I have to do is every time I make my cup of tea at 3 o'clock, I eat an apple, and then after a while that'll become automatic and I'll pick up the apple without thinking of it.
Well, yes, I mean, that's what we'd suggest. I mean, the more specific your plan, the better. I mean, it is better to think about, for example, when I'm going to make my cup of tea, I will say eat an apple, or, to tie it to something that you already do, rather than to say, for example, in the afternoon, I will eat an apple. So yes, if you want to do the behaviour repeatedly, then it's a kind of generic principle of behaviour change. Set yourself a plan and be as specific as possible and realistic as possible within that context of that plan.
Now, I've read in quite a few places that it takes 21 days for something to become a habit. So I'd have to spend 21 days remembering to eat an apple with my tea, and then it would become automatic. Is that true? And where did that idea come from?
That's a very interesting concept. I mean, given how kind of well-known and pervasive this notion of it requiring 21 days to make a habit is, you'd expect that there's a solid body of evidence behind that. But in fact, as part of my work, I actually looked into the kind of evidence base for this, and it actually comes from a book that was written by a plastic surgeon in 1960. It was a self-help book. It wasn't a kind of scientific text, so it didn't kind of undergo peer review or anything. It was just based on his observations that among his patients, it tended to take them 21 days to get used to their new appearance. And he also then kind of extrapolated from that and said, well, actually, it seems to take about 3 weeks to become used to being in a new house, for example. And from that, this entire thing has kind of snowballed, and we're now in a situation where it's kind of assumed that it takes 21 days to form habit. There's an intuitive appeal to it, but unfortunately it's not baseless, but, it's based on very weak evidence indeed.
So is there any evidence as to how long it does take for these habits to form?
Yes, I mean, within our department, we did a study recently that suggested that it takes on average 66 days for habit to form, but that comes with a number of caveats. I mean, within this study, this was a study that was done where 96 postgraduate students were participants in the study. They were asked to choose a behaviour that they wanted to do, a new behaviour. So that could be a dietary behaviour or a physical activity. And they were asked to just do that behaviour once a day, every day, for a period of 12 weeks. And they had to choose a particular context in which they do it. So, for example, after breakfast, I will go for a walk, and so on. Now, what the participants had to do was they had to not only do the behaviour, but each day they had to log onto a study website to log whether they'd done the behaviour and also how automatic the behaviour felt. So that gives us that measure of habit as we as psychologists define it. And what we actually found was there was massive variation in how long it took for people to reach their kind of plateau of habit strength. In other words, as automatic as this behaviour was going to become. In fact, the median value was 66 days. So that's really the kind of headline finding. But if you dig a little deeper, something that I'm eager to put across is that actually there was a massive variation in how long it took for people's automaticity or habit strength to peak. There were some people that reached the plateau of their automaticity within just 18 days. There was one person who didn't reach their peak at all within the 12-week period, but it was forecast that if they carried on doing the behaviour, it would take them 254 days. So as you can see, a massive range. And there was also variation in the level at which the habit peaked. So for some people, it would peak around the midpoint of a scale, a 0 to 42 scale that was used to measure habit. For some people, it peaked there, whereas for others, it peaked at the very top of the scale, suggesting that some people could actually form stronger habits than others. But why there should be that difference, we're not really sure.
So more research to do there. Thanks so much. That was Ben Gardner from the Health Behaviour Research Centre at University College London.
Now, perhaps your New Year resolution was to go on a diet and to strip off some of those extra pounds you put on from eating and drinking a little bit too much over Christmas. Well, with Christmas and New Year now behind us, many people are probably ruining the amount they actually ate. But why do we crave and thoroughly enjoy sweet things? Well, thanks to New York scientist Jeffrey Friedman, we now understand a little bit more because he and his team have discovered a population of nerve cells in the brain that communicate with each other using a nerve transmitter chemical called melanin concentrating hormone, MCH, which are the neurological bases for the brain having a sweet tooth.
Sugar is a very attractive nutrient for two reasons. One, it tastes sweet, but it's also attractive because it has nutrient value. And it's actually the nutrient value of sugar, meaning its ability to provide calories, that explains a lot about why sugar, or sucrose in particular, is preferred to artificial sweeteners which don't have any nutrient value.
But I put it to you that lots of people do drink diet drinks, or they do add sweeteners. So they obviously do think that the flavour is quite nice. So when you do subvert your sense systems into experiencing a sweet taste with no calories in it versus glucose, which is obviously more calorie rich, how does the brain respond to that?
If animals are given the choice between a natural sugar like sucrose or an artificial sweetener, they invariably prefer the natural sugar. The same is probably true in humans because all the statistics would seem to indicate sweetened sodas outsell diet sodas by a great margin. Now, it's true that many people use artificial sweeteners, and in the short term, of course, they'll find that satisfying, but what that doesn't tell you is whether they might go back and have sucrose in some other form later on, in the form of a candy bar or a candy. And it certainly seems as if a lot of the intake of sugar and nutrient in general is unconscious and is driven by signals of the nutrient value that is present in our food.
Now, what actually detects that nutrient value then? So when I put something sweet into my mouth, is it just the sweet taste, and there's therefore a neurological inference of the calorie value of what I'm eating? Or is there integration of multiple analyses of the food, the calories coming in plus the sweet taste? Or is the brain just looking at blood glucose and going, I ate that Mars bar, therefore the sugar's gone up, therefore it must be good for me?
The answer appears to be both. So certainly a sweet taste, such as either in a sucrose or an artificial sugar, is attractive. But it's attractive because it predicts that that nutrient or that compound you just ate will have calories or nutrient value in it. But if that taste is empty of calories, it won't be reinforced. What reinforced the desire to eat sweet things is ultimately the presence on top of it of calories, which are to some extent thought to be sensed by increasing the level of glucose in the blood. Unknown till recently, however, was where and how that glucose increase in the blood is sensed.
So how did you probe that?
A very talented colleague of mine, Ana Domingos, hypothesized that a particular nerve cell population in the brain, referred to as MCH, melanin concentrating hormone, might have something to do with the sensing of sucrose and why it is preferred to sucralose. The reason that Ana hypothesized these neurons might play a role in sugar sensing is because, firstly, the neurons can be shown to fire more rapidly when exposed to sugar, and secondly, because if you kill these neurons, animals lose weight and weigh less. And those two published findings led her to hypothesize that perhaps these neurons played some role in the sensing of sucrose and establishing a preference versus an artificial sweetener.
Do you think that sensing goes on when the glucose, which has come from the sucrose, goes into the brain? Or do you think that there are sensors for sweetness in the tongue, perhaps even in the intestine, and they're telling those MCH cells in the brain, hey, I'm being stimulated by something sweet?
So the experiment Ana did was, in the first case, kill all the MCH neurons. And if she did that, animals could no longer distinguish between sucrose and sucralose. They now had an equivalent preference. Conversely, if she activated those neurons using some new experimental tools, she could switch an animal's preference to the artificial sweetener if it was linked to the activation of those neurons. This tells us pretty definitively that these neurons play some role in the sensing of sucrose, but it doesn't actually tell us whether or not the glucose itself or the sucrose itself is actually being sensed by these neurons or by some other group of neurons, such as sweet sensors elsewhere in the body.
Where are these MCH neurons, and what, more importantly, perhaps, do they connect to?
MCH neurons are present in a brain region known as the hypothalamus, in a particular region of the hypothalamus known as the lateral hypothalamus, and this nucleus is generally thought to activate hunger. This particular hypothalamic region is intimately connected to reward circuits that play a role in changing the motivation for certain behaviors or certain preferences. And so they're well positioned both to sense glucose signals directly or indirectly and then connect them to reward circuits.
So now you know. That was Jeffrey Friedman from Rockefeller University in New York. We asked you at the beginning, why do plants make nicotine? We like, in some cases, to smoke it because it is addictive. But why does a plant need it? Well, the answer is it's a very potent neurotoxin if you're an insect. And so it's a plant's own inbuilt form of insecticide. That's the answer to the quiz. Ginny.
Our guests for today are Molly Crockett and Ben Gardner, and they're going to answer some of our questions we've had in from listeners. So Ruth asks, are you more likely to achieve your resolutions if someone else has the same ones? So if you hook up with a running partner or you have a housemate who's on the same diet, does that help? Molly, what do you think?
I think absolutely, for several reasons. One is that you've got two minds and two sets of willpower working together to help you both achieve your goals. Two, one of the most powerful motivators is social reputation. We really, really care about what others think about us. And it turns out also that having others think of us as being self-controlled is also a really good thing. So that just adds an extra boost to the motivational processes behind your resolution.
Ben, anything to add?
I quite agree. I think it is really about keeping that motivation high, because given that to form a habit you need to repeat a behaviour consistently, one thing that people don't often realise when they're embarking on a habit formation attempt is that they'll have to repeat the behaviour, so they need to keep going at it. So anything that can boost your motivation in that respect must be a good thing.
Ben, we've heard from Joe on Facebook, and he says, why do we have willpower for about a week and then we give up? Do gyms use this period of enthusiasm and take it into account when they're drawing up contracts for new members?
Well, I mean, I can't actually speak for gyms, but I think this relates to the answer I just gave. I think that people often are willing to put in the effort at the start, but they don't actually have kind of realistic forecasts of what's going to be involved in doing a behaviour. It might be that they don't adequately plan how they're going to, for example, keep going to the gym. It's one thing to plan when and where you're going to start going to the gym, but you need to make sure that you have this plan for keeping it up. And I think that's the problem, that people just find that actually they can lapse back into their old habits and routines. And if they don't plan adequately to cope with those kind of obstacles, then they will lapse. And so that will be experienced as a kind of dip in our willpower.
Molly, what do you think?
I think the thing to add is that this time of year, willpower and making resolutions is at the forefront of everyone's mind. It's central to our attention. And so it's easier to sort of think about and plan for those goals when it's at the front of your mind. But distractions tend to creep in, and that can interfere with the goal-directed process of trying to achieve those goals.
So Jen wants to know, what stops us from making changes at a random time of the year? So maybe when we first think that we should start eating more healthily. Why don't we do it then? Why do we wait until there's some kind of milestone? Ben, do you have any ideas?
I think it may be that we need often a kind of what's thought of as a cue to action. We need something to give us that push to actually start making changes to our behaviour. So something like, for example, for smokers, non-smoking day, or, for example, someone who wants to make a major change in their behaviour, the January resolution kind of window can help with that.
Molly, have you got any ideas on that one?
I think perhaps the added social pressure of everyone else talking about their resolutions and what goals they're looking to pursue in the new year could help provide an extra sort of boost in motivation.
We've got an email here from Sue Bauman, who says she thinks that most New Year's resolutions will fail because people set unrealistic goals without the right support in place. Is this destructive to people with difficulty around addiction and habits, etc.? She wonders. Molly, what do you think?
I think I would agree that you're more likely to keep your resolution if you make it manageable. There's a researcher at Stanford named B.J. Fogg who has done some work on this and shown that you just need to establish a habit in order to carry on with the resolution, but you're much more likely to do that if you start really small and manageable, and actionable items are really important.
Ben?
Yes, I think I'd agree with that. I think smaller changes are always better when it comes to kind of sustaining behaviour change. So certainly start low, go slow is one slogan that's often used to kind of describe that. We need to look at making quite small changes and then aim to help those to build up so that we can manage the larger changes, but by going slow.
Now, Josephine Ong wants to know whether people who have addictions to sugar, for example, are more likely to be susceptible to other kinds of addictions. So I guess this is the kind of idea of addictive personalities. Do you know anything about that, Molly?
I'm not an expert on this, but I do believe that there's some evidence that the structure of your dopamine system in the brain can make you susceptible to different kinds of addictions. This work was done actually by Barry Everett at Cambridge and Trevor Robbins and that group. They found that, for example, a certain type of dopamine receptor in the striatum, the density of that receptor can make rats more or less susceptible to addictions. But I'm not sure the extent to which we know this in humans.
I think there was also some work that suggested that rats that were more impulsive were also more likely to become addicted. So they have a little test where when a light flashes on, the rat has to poke its nose in the box that has the light in order to get a reward. And rats who are likely to poke their noses in boxes before the lights came on, so were impulsive, seemed to be more likely to become addicted when they were given drugs. Again, I don't know if that applies to humans yet or if it's just in the rat models.
I think, yeah, absolutely. That work also has been done in Cambridge, and I think it has been extended to humans. That you can see in addicts that measures of impulsivity similar to the test with the nose poke and the light. People who are addicted to various substances are more impulsive on those kinds of tests, certainly.
Molly, we've got a comment here from Caroline Trett. And it's interesting because, of course, your study looked at men's susceptibility to being seduced by the charms of attractive young ladies. Well, she says, I get really strong cravings for sweet stuff at a certain time of the month, and I cannot focus on anything apart from satisfying this urge. Now, I know it's obviously the opposite sex, but is there anything in sort of menstrual cycle and resolution ability to have willpower?
I don't know the answer to that question, actually, but certainly the hormonal systems associated with the menstrual cycle interact with the dopamine system in the brain. This is work by Emily Jacobs and Mark Desposito. That has been done in the context of working memory, I believe, but we do know that dopamine interacts with estrogen, so it's certainly plausible that this could be the case.
Ben?
The only thing I'd add to that is perhaps that actually the expectation that certain time of the month will lead to these particular cravings could have actually created a habit in more of the sense that I was referring to, whereby experiencing that particular stimulus, in other words, that time of the month, actually triggers that craving, and that may be occurring on top of any chemical changes.
And also, it sort of chimes with what Barry Everett was saying earlier about when he comes out of his front door and he's in a street that he recognises and it normally is the way to work. On a Sunday, he sometimes ends up in work by accident. It's sort of, if you've got the environment set up around your menstrual cycle, there are lots of cues there that might cue you to want the sugar rather than purely the hormones.
Yes, I'd quite agree with that, yeah.
Thank you very much to our guests this week, Molly Crockett and also Ben Gardner. Well, on the subject of tough to answer questions, here's our question of the week with Hannah Critchlow.
This week we get hypnotised by light, taking a squiz at this question that Lee wrote in with.
How and why are bugs attracted to bright light?
So there's not many bugs around this time of year, but those that are seem to be collecting by my kitchen light. So why is that? Ian Burgess, director of the Insect Research Group in Cambridge, has this to say.
To be quite honest, the short answer is nobody knows. There are lots of theories, and some of those are a bit more logical than others, but most of them are definitely speculative, and others are definitely disprovable. What we've got are things like moths mistaking light for the moon. And the reason for that is because some moths that migrate position of the moon to orientate which direction they're travelling in. But that doesn't explain why non-migrating moths, which is the vast majority of them, and other insects actually get confused by lights because the moon has no impact on them at all. Others suggest that maybe they get dazzled. Well, that can't happen at a distance, and a candlelight or a campfire or even a spotlight, if you're half a mile away, doesn't look very bright. Some people suggested that the pheromones that female moths emit produce a faint luminescence, and that male moths can detect light in the environment and confuse those with the luminescence from the pheromones. But of course that only applies to males. What about the females? Well, it seems that wavelength is important, and they found that the new white or bluish-white lights that are used for street lamps actually are more attractive to moths than the sodium lights, the yellow ones that we've had for years. But it doesn't explain why insects that have been adapted for millions of years of evolution to fly around happily in the dark are quite normally conditioned to hide away from light during the day, then suddenly suicidally rush towards illuminated objects like cars and street lamps that are none of their business.
And it's not just moths. If you go to the tropics, streetlights are covered with termite swarms. And sorry, Lee, we've been trying to illuminate the issue of why they do this, but we don't really know the answer to why bugs collect around lights. Well, we next turn our steady gaze to the skies with this.
Hi, my name is Ray Gorman, and I live in Astoria, New York. Greetings, naked folks. Does the expansion of space slow the speed of light? So if you're looking at the universe from the outside of the universe, would the distance of a mile a few billion years ago be less than what a mile is today? This would make the speed of light slower back then compared to now, wouldn't it?
So, if the universe is expanding, does this affect the speed of light or time?
Hannah Critchlow, and if you think you can help Hannah, then do get in touch. The email address is chris@thenakedscientists.com for your suggestions, which you may also tweet to @nakedscientists, or you can find us on our Facebook page as well. And if you have any questions for The Naked Scientists, or thoughts or feedback, the same address applies. We hope you'll join us at the same time next week when we'll be finding out all about the future of space weather forecasting. The UK is one of the first countries to actually begin publishing a forecast of the conditions created around the Earth by the sun. We'll hear why they're doing that from our own Science Minister, David Willetts, and we'll also find out how the sun affects the world in the first place. Our production this week was by Dominic Ford and Kate Lamble. Thank you very much to Ginny Smith for joining me. This is The Naked Scientists, which comes to you from Cambridge University. It's supported by the STFC, the EPSRC and the Wellcome Trust. I'm Chris Smith, and until next time, goodbye.